Today's lesson is on scientific notation. Scientific notation is just a way that we can write very, very large numbers or very, very small numbers. So here we have a very large number, and then instead of writing that number that way with that many zeros, you can write it in scientific notation, which is the same representation, just a little bit different. And then here we have a very, very small number that we can write in scientific notation instead. We are able to do this because both of them are being multiplied by a power with base 10. And think about anytime you multiply a number by 10, what happens? So let's say you have 3.4, and if you multiply by 10, what you're really doing is just moving the decimal. So that equals 34. Or what if you had 3.4 and we're multiplying by 10 squared? That's 2 tens, or times 100. You move the decimal once and then one more time, so it would be 340. So we're basically writing it in a way that we're multiplying the front numbers by 10. So now let's go into our actual notes where you learn the proper form of scientific notation. Proper scientific notation is always a number a times 10 to the power of m. So, first, the number in front, a, it has to be greater than or equal to 1, but less than 10. And then m can be any number, both positive or negative. So, if it has to be in this form, let's look at a couple different examples and decide if it's proper scientific notation. Here are 3 examples, and we have to decide which one is actually in the proper scientific notation. So let's look at this first one. 32 times 10 to the power of 3. Is 32 in between 1 and 10? It is not, so this is not proper scientific notation. Is 0.6 between 1 and 10? No, it is not, because it's less than 1. Which leaves us with this last one. This is proper scientific notation because the front number is in between 1 and 10. So there we go. Today's lesson is about converting between scientific notation and standard form being just a regular number. So we're going to look at numbers that are in scientific notation and change them to standard form. The first one is 5 times 10 to the power of 4. So there's scientific notation. We need to write that in standard form. And this exponent, 4, tells you to move the decimal 4 places to the right. So if the decimal is technically here, we would move it to the right 4 times. And every time you move it, you're adding a 0. So you'd have 5, add 1, 2, 3, 4 zeros, so it would be 50,000. And then we can check, let's see, 1, 2, 3, 4. Good. Let's look at these next 2 examples. First we have 3.2 times 10 to the third. So we have to move the decimal 3 times. So here if we move it once, we have to move it 2 more times past the 2, which means we add 2 zeros. So we have 3, 2, add 2 zeros. And you can always check, my decimal was here, now it's here, and count 1, 2, 3. Good. And then this third one, we have to move the decimal 5 times. And here we have to move it twice until we get to the end, which means we have to move it 3 more times, 1, 2, 3, which means we have to add 3 zeros. So we have 2, 5, 2, and then we're adding 3 zeros. And then let's see, let's put our commas, count by 3s, right there. And then check your answer, 1, 2, 3, 4, 5. Good. want you to now write these down, pause the video, and try these three on your own. Here you should have gotten 923, and then here we should have 670 million, because you move it once past the 7, and then you should have 7 zeros left over to write. And this last one, 1,546.7. Now, still dealing with positive exponents, we're going to go backwards. I'll give you a number in standard form, and we have to change it to scientific notation. So let's look at our first example. 50 million. So how can we write this in scientific notation? Well, I know it's always a number times 10 and then to the power of something. So we always have times 10. What you do is start from the left, always put a decimal after the first number, which is 5. So that's our first number here, 5 times 10 to, and now count how many times would we have to move the decimal. 1, 2, 3, 4, 5, 6, 7. 5 to the times 10 to the power of 7. So in this one, 6,800,000, from the left put a decimal right after that first number. So instead of just 6, we have 6.8. So 6.8 is my front number, times 10, and we have to figure out to what power. Now, common mistake is students just count the zeros, because in this first example, our exponent was 7 and we had 7 zeros. But really what you're counting is how many times do you move the decimal. So we move the decimal 1, 2, 3, 4, 5, 6. So it's 10 to the power of 6. And in this case we had 5 zeros, so it is different. Okay, example number 3, 1,230. Put the decimal right after the front number. So then we have 1.23, and then times 10 to what power? We would move the decimal 1, 2, 3 times. Here are 3 more examples. Why don't you pause the video, write them down, and see if you can figure them out on your own. Here are your answers. I hope you did well. Now, we're back to going from scientific notation to standard form, but this time we have negative exponents. Remember, positive exponents mean very, very large numbers, and negative exponents mean very, very small numbers. So here we have 5 times 10 to the power of negative 3. The same thing as before, the exponent tells you how many times to move the decimal, except in this case we're going to move the decimal the other way. The decimal is technically to the right of the 5, and we're going to move it to the left. So we move it once, and then 2 more times, and then we have to add 2 zeros. So 0, 0, 5, and I always put a 0 in front. So if we check our answer, 1, 2, 3 would get us back to 5. Now what I always do, the reason I always write this number in front, because it will always match up 3 and 1, 2, 3, 3 zeros. With the negative exponents, as long as you write the number in front, the number of zeros will match up to your exponent. So now we have 7.9 times 10 to the negative 5. That means that you move the decimal to the left 5 times, but it also means that you have 5 zeros. But you can only count 5 zeros if you put the decimal in between the first 2, and then you can write the numbers that you have in order, so 7, 9. So in this case, 2.71 times 10 to the power of negative 6. Exponent -6, so I'm going to count 1, 2, 3, 4, 5, 6 zeros, decimal in between the first two zeros, and then I just list my numbers, 2, 7, 1. Now I'm going to give you 3 more examples. I want you to write them down and see if you can figure them out on your own. Okay, check your answers. 0.084, 0.58, and 0.00066. This will be our last set of examples. This time switching and going from standard form to scientific notation using negative exponents. So the first example, 0.00021. So what we want to do is first write, remember you always write a front number and then times 10 and then to the power of something. So what is our front number going to be? You always, from left to right, as soon as you have the first number other than 0, you put a decimal. So it's 2.1, and then you count how many times you move the decimal. 1, 2, 3, 4. Or you could count how many zeros you have. 1, 2, 3, 4, counting the one in front. So that means your exponent is not 4, but -4, because it's a very small number. Okay, next example. 0.0000005. So, the first number other than 0 is 5. So 5 is my leading number, and then times 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, but it would be -8. Next example, 0.209. So in this case, the first number other than that front 0 is 2. So 2 and then decimal, whatever we have left, 2.09 times 10 to the power of, how many zeros are in front of the 2? Just the 1, so -1. Here are the last 3 examples. Why don't you write them down, pause the video, and try them on your own. Check your answers. You should have 6.31 times 10 to the power of -4, 9 times 10 to the power of -2, and 4.8 times 10 to the power of -3. So there are all the examples of scientific notation changing back and forth between standard form and scientific notation. Just remember, these are all ways of writing very, very large numbers or very, very small numbers. So, good luck with your lesson.